This video is about triple integrals. First of all, why we want to learn triple integral? Think about the problem like this. I give you a solid. Okay. This is a solid. Okay. Three-dimensional things. Now we want to find, for example, we want to find the mass of this solid. If we do know, if the density, okay, if this is the density function, x, y, z, okay, at every point you have like the density could be different. So for this kind of problem, how do we find the mass for this given solid? We use, the problem is the density is not constant. Okay, so same idea. We break this solid to many small cubes. Okay, so we call the volume of this cube, we say dA. Then make this cube small enough so we can treat the density as a constant. So fx, y, z, which is the density times, dV. Let's now say dA, dV. dV is the volume of this small cube. Okay. If this cube is small enough, we can think about fx, y, z is a constant. Okay. So we'll give you approximation for the mass for that cube. Then add them together. We have so many such cubes. Okay, you have so many such cubes. Add them together would give you the approximation for the mass of this whole thing. Okay. Then if you take a limit, without taking limit, it's just approximation. Take a limit, let the volume go to 0. Then this would give you, that's what the definition for triple integral. We call this solid region, say E. fx, y, z, dV. Okay. That's the definition for the triple integral. Okay. If you want to think about its application, find the mass is one of those. Okay, the next question. How do we calculate this triple integral? This is very similar to, just try to recall, how do we find the double integral? We write double integral to we can write as two iterated integrals. Same thing here. Okay. Think about we'll have some solid like this. This is our solid E. Okay, we want to write as iterated integral to calculate it, just like a double integral. So first thing we need to describe all the points inside of this solid E. Okay, now let's make a projection of this solid on the xy plane. Then you got a region D on the xy plane. So this region D tells you any point in this solid, they have the xy coordinates lie in this region D. Okay. So one more thing we need to figure out is what is the restriction for Z. Okay. See, anything in this tube, they have the xy coordinate fall into the D. Okay. So pick any point in this region. Okay, see what is the restriction for D, okay, for Z. For this one, for the given xy, your Z will be bigger than this point hit on there's two surfaces here. One is this bottom one is this top one. Okay, so your Z will be bigger than this point hit on the bottom surface and less than the one hit on the top surface. So for all the Z in between, those points will be inside of region E. Okay. So how do you find your z is bigger than this point, less than that point? Okay. So what is that point? For given x, y, you hit this bottom surface. Okay, this is my bottom surface. This surface, say, okay, remember what is the surface? Z equal to, say, g1 xy. Okay. And your top surface is given by z equal to g2 xy. Okay. So your xy is on the region D. Okay. Your z is bigger than g1 xy and less than g2 xy. fxy z, then you have dz. Okay. Z is between those two. Then you have dA. Okay. So after you have done this, you change your triple integral to a double integral. So once you get a double integral, we can use the things we learned before to find that double integral. Now let's look at an example. Okay, we want to integrate this triple integral. Z dv. Okay, what is my E here? My E here is a tetrahedron bounded by 4 planes. One is a plane, one is xz plane, another is xy plane and yz plane, and one more plane is this one. This one is x plus y plus z equal to 1. Okay. So we have 4 planes: xy plane, yz plane, xy plane, and plus this one. Those 4 planes bounded a solid region. Okay. This region is this tetrahedron. Okay, that's our E. Okay. Now we want to integrate this triple integral. So as we explain, first things we need to do is change this triple integral to a double integral. So how do we do that? From z-axis, look down of this solid, make projection on the xy plane. You got your region D. For this case, this shaded region is a triangle. It's not hard to see. Okay. So let me draw that one here. You got a triangle like that. That's our D. Okay. Okay, so this can be written as a double integral, and then you have dz, then you have dA. Okay. Now the question, what is the restriction for z? So let's pick the point on this region D. Okay. Then just make a line like this. Okay. The z is bigger than the one on the bottom plane and the heat on the top plane. Okay. So your z will be bigger than the bottom surface. What is the bottom surface? This bottom surface is z equal to 0, right? It's the xy plane. Then your z is bigger than that. Keep up until they hit this surface. What is that surface? Which is this plane. Okay. So your bottom surface is z equal to 0. Your top surface is z equal to 1 minus x minus y. Okay, now, so you integrate the inside one with respect to z, give you 1/2 z squared evaluated at 0 and 1 minus x minus y dA. So give you 1/2 1 minus x minus y squared dA. So this tells you how we can change a triple integral to a double integral. Once you get a double integral, let's go back to what we learned before. Okay. So this double integral is on xy plane in this triangle. Okay. So first thing we need to figure out what is the equation of this line. Now let's go back. This line is this one. Okay. How do we find that line? That line is intersection of two planes. One plane is z equal to 0. Another is x plus y plus z equal to 1. So the intersection of those two give you a line. This line is substitute z by 0, give you x plus y equal to 1. Okay. So that's the equation of this line. Okay, now let's go back to double integral. Okay. So for given region D there, how do we describe this? Now you can change your dA either dy dx or dx dy. For this case, doesn't matter which way you go first. Okay. Now let's go dy dx. So dx, always look at the variable is outside, which is x. So make the projection of this triangle on the x-axis. Smallest x will be 0, largest 1. Okay, intersection of this curve, y equal to 0, x is 1. Okay. So your x is between the smallest x and the largest x is 0 to 1 for all the points in this triangle. Okay. Then go up, fix x. Then your y, see all the point here. Your y is bigger than 0, less than that point. Okay. Right, here's a 0, always 0. Less than that point. That point depends on x. So for giving x, you can solve the y is 1 minus x. Okay, now we can do this. Integrate about y. Okay. Treat x as a constant. So this give you 1/2 times 1/3, 1 minus x minus y to the third, with there's a negative here, so you got a minus there. Okay. If you have confused with that, you go to the how to integrate a single integral. Evaluate at 0 and 1 minus x dx. So this gives you negative 1 over 6, 0 to 1. Okay. Whenever you see, this is integral about y. Okay. Whenever you see y there replaced by 1 minus x squared, then minus the third, then 1 minus x minus replace y by 0 to the third. Okay, this whole thing's dx. Okay, this is a polynomial. It's easy to integrate it. After you integrate it, you got 1 over 24. Now let's look at another example. This example, we want to find triple integral. E there, then the function we try to integrate it is x squared plus z squared dv. Okay. My e here this time is part of a paraboloid. Okay, this is a paraboloid. Y equal to x squared plus y squared. This goes all the way there. But we just want to part of that. Cut here. Here, y is 4. Okay. So this shaded region is our E. Okay, now to calculate this triple integral, we need to write as iterated integral. First of all, change it to double integral. We have several ways to do that, just like double integral. So, like what we did before, what you can do is project this solid region on the xy plane. You can imagine you will get a parabola like this. Okay, so this parabola will be a region D. Let me write this. So this triple integral can be written like this. D here, then you do this. Fixed point here, you go up and find out your z is bigger than this point, hit on the bottom surface, and the end of that point, which is hit on the top surface. So you have to figure out what is the bottom surface and what is your top surface. For given xy, we want to find z. Obviously, this point is on this paraboloid. Your bottom surface is a part of a paraboloid, so is the top surface. So for knowing x and y, we want to solve for z. This is z, sorry. Solving for z. So your z there equal to positive and negative square roots y minus x squared. Again, if you take positive sign, you got top surface. Z equal to square roots y minus x squared. If you take bottom part, z equal to negative square roots y minus x squared. So bottom surface, negative square roots y minus x squared. And the top one, y minus x squared. Then you have this. Then dz, then the whole thing, then dA, okay. Your d there is a parabola like this on the xy plane. Here is the 4. This is your d. And you are going to see this is not easy integral. Okay. Now if you are lucky, you can integrate this, find what you want. Okay. However, for this problem, we have another option. We don't have to project our region to the xy plane first. Just like a double integral. Okay. We got several iterated integrals. Sometimes one is easier than the other. Same thing here. Here is a 4. Okay. Okay. Now, if we want to project on the xz plane, what kind of region do you think you are going to get? Try to imagine that. Which is not hard to find. You are going to get a circle, right? On the xz plane. We call this circle region is D there. Okay, the same triple integral E. What is function? Square roots x squared plus z squared dv can be written as over D there, then okay, we'll project on the xz plane. Okay. Then you go any point. That means all the points in this solid E here, their x and z must fall in this circle. Okay. So we find restriction for x and z. Now let's find restriction for y to make such a point in this solid. Okay. So you fix any point xz here, any point xz here. You go there. Okay. Now, what is the restriction for y? And your y should be bigger than some point hit on the bottom surface and less than the point for your y hit on the top surface. Okay. So what is this bottom surface? obviously this is paraboloid, right? For giving xz, your y there is, okay, this paraboloid is y equal to x squared plus z squared. Okay. So that's your bottom surface of integral. Y is for giving x and z, like that. Okay, what's your top surface? Top surface is this one, right? What is this surface? Y equal to 4, which is a plane, parallel with xz plane. So y equal to 4 is your top surface. Okay. And then you have dy, then whole sense dA. For this problem, if you use second way to do it, your integral, you're going to see your integral is much easier to integrate it. Okay, now let's integrate the inside one. The inside one is about y, so you treat xz as a constant. Therefore, they give you x squared, square root x squared plus z squared, and times y, evaluate at 4, and x squared plus z squared, then dA. Okay, this is equal to square root x squared plus z squared, replace y by 4, subtract, replace y by x squared plus z squared, dA. So now we change the triple integral to a double integral. Let's go back to see what is the region D here on the xz plane. Okay. Xz plane. And we can see that it's a circle. Okay. It's a circle. This circle is this one. So what is, and this circle is what? Same as this one. So what is radius? Y equal to 4. Intercept with that. This circle is intersection of two curves, two surfaces. One is this paraboloid. One is a plane, y equal to 4. Intersection gives you x squared plus z squared equal to 4. So your radius is 2. Radius is 2. Okay. So for this kind of integral, it's easy to do that by using polar coordinates. Okay. So if we do polar coordinates, x squared plus z squared just give you r. Then you got a 4 minus r squared, change your dA to r, dr, d theta. Okay. And for this region, your theta obviously from 0 to 2 pi. And then your r, okay, this circle formula in polar coordinates is r equal to 2. Okay. So for giving fixed theta, your r is bigger than 0, less than 2 always. Okay, so integrate this. You got 4r squared minus r to the 4th dr d theta. Give you 0 to 2 pi. 4 third r to the 3rd minus 105 r to the 5. 0 to 2, I forgot that, sorry. 0 to 2. And after you integrate that, you can calculate that they give you 128 pi over 15. Okay. One more thing I like to say is, if this one give you the area of D Then similarly, triple integral give you the value of E.